Welcome to part 1 of this video playlist about the best methods to acylate amines for the preparation of amides. This first presentation is about the use of acyl halides as acylating reagents. Acyl halides are inexpensive and highly reactive electrophiles and can be used to acylate even unreactive amines, such as diaryl amines. But also for less demanding amines, acyl chlorides are often the most readily available and effective reagents for preparing amides, for instance by the Schotten-Baumann procedure in water or aqueous solvent mixtures. Amides show strong dipole moments and hydrogen bonds, and these often define the overall physicochemical properties of compounds containing this functional group. Because the carbon-nitrogen bond in amides has some double bond character, rotation of this bond is slow on the NMR timescale, and DMF and DMA give two distinct signals for the two nitrogen-bound methyl groups. In some amides, these signals just start to coalesce at room temperature, and the proton NMR spectra of acylated secondary amines with two different alkyl groups at nitrogen often give broad, not very informative signals, even for pure products. Acylated primary amines assume preferentially the anti-conformation. Therefore, it is often difficult to perform cyclization reactions of such amides, which rather tend to oligomerize instead of cyclizing. Intermolecular hydrogen bonds and dipole-dipole attraction are the main reasons for the high boiling and melting points of most amides. Comparing the boiling point and water solubility of dimethylacetamide with that of a ketone, ester or amine of similar size shows the impact of the dipole moment on these properties. Dimethylacetamide boils at a much higher temperature than, for instance, methyl isopropylketone or methyl acetate, and is also miscible with water. Still higher is the boiling point of acetamide, more than 100 Kelvin higher than that of acetic acid, which also forms intermolecular hydrogen bonds. Thus, the amido group is a very dominant functional group, with a strong impact on the overall properties of a given molecule. Amides are remarkably stable toward nucleophiles and acids. In this example, an acetanilide was partially cleaved by treatment with hydrazine in DMSO at 100 degrees Celsius, but anilides are more sensitive toward nucleophiles than N-alkyl amides. The latter are really difficult to cleave under basic reaction conditions. Acidic conditions are usually better suited for the hydrolysis of amides, but still high temperatures and long reaction times are often required. In this example, N-acetylpyrrolidine was hydrolyzed with 20% aqueous perchloric acid at 82 degrees Celsius, and the reaction took several days to go to completion. Some amides are useful compounds and are prepared on a large scale. In addition to polyamides and polyimides as polymers for many applications, amides like dimethylacetamide, DMF and NMP are commercially important solvents. Also, caprolactam is manufactured in huge amounts as starting monomer for the preparation of nylon. The solvents DMA, DMF and NMP are prepared as shown here. Methylamines are obtained from the methylation of ammonia with methanol, and acylation with methyl acetate, carbon monoxide and gamma-butyrolactone yields the corresponding amides. Thus, as in most industrial processes, no halides, but only water is produced as waste. Epsilon caprolactam is prepared by Beckmann rearrangement of cyclohexanone oxime, again a waste-free transformation. Then, a number of technically relevant amides, such as nicotinamide or acrylamide, are prepared by hydration of nitriles, which in turn can be obtained by amoxidation of alkanes. The acylation of amines is the most straightforward method for preparing amides. But occasionally, some specific amides can be prepared more readily by some alternative synthesis. One of these alternatives is the Ritter reaction, in which nitriles are alkylated by a carbocation and converted into N-alkyl amides. This reaction can even be conducted with methanol as alkylating reagent, which does not form carbocations readily. Then, if a given amine is unreactive, it may still be converted into a carbamoyl chloride by treatment with phosgene, which is an extremely reactive electrophile that cannot form ketenes. The intermediate carbamoyl chlorides can then be treated with numerous carbon nucleophiles to yield the expected amides. Isocyanates react similarly with carbon nucleophiles, for instance with polar organometallics or enolates. As alternative to carbamoyl chlorides, formamides can also be used as starting material for the preparation of amides. In this case, in addition to the carbon nucleophile, an oxidant is also required, either during the reaction or in a second step or during workup. Alternatively, if noble metal catalysts are used and the reaction temperature is sufficiently high, a spontaneous dehydrogenation can occur. Finally, certain catalysts and oxidants can oxidize amines selectively to amides. This is, however, a difficult reaction and only few successful examples have been reported. Potential byproducts include imines, imides, enamines, dealkylated amines or amine N-oxides, and their formation is often difficult to prevent. The textbook mechanism of the acylation of amines by acyl halides is an addition of the amine to the carbonyl group followed by dehydrohalogenation as shown here. Acyl halides with at least one hydrogen atom in the alpha position, however, are strongly CH acidic and readily eliminate hydrogen halide upon treatment with aliphatic amines. The resulting ketenes are still powerful acylating reagents that will quickly react with most amines. But if the amine is unreactive or its concentration too low, ketenes may also dimerize or react with other nucleophiles present in the reaction mixture. At the end of this video, I'll show you some further potential side reactions. Acyl halides are sufficiently reactive to acylate amines under acidic reaction conditions. Nevertheless, only the unprotonated fraction of amine can be acylated, and the rate of acylation will therefore drop if the excess of acid gets larger and if a more basic amine or stronger acid is chosen. The main advantages of acylations conducted under basic conditions include the good solubility of both reactants in aprotic solvents and the high reaction rates. Problematic are, however, the potential formation of ketenes and the need of at least one equivalent of a base to neutralize the released hydrogen halide, which would otherwise convert the starting amine into an unreactive ammonium salt. If no base is added, or if an ammonium salt is used as starting nucleophile, then the choice of solvent becomes more difficult because most ammonium salts are not well soluble in aprotic solvents. Moreover, because of the low concentration of free amine, higher reaction temperatures are usually required to attain complete conversions in a reasonable time. The advantages of this strategy are that even base labile acyl halides can be used, for instance those with a high tendency to form ketenes. Furthermore, no additional base is required and the released hydrogen halide can be collected or neutralized with some inexpensive aqueous base. I'll show you some examples of both strategies in a minute. The most common acyl halides used in organic synthesis are acyl chlorides, but occasionally fluorides or bromides may offer some advantages. As shown here, acyl fluorides are much less reactive than chlorides and have been used as mild, highly selective acylating reagents, for instance for the synthesis of peptides. Acyl bromides, on the other hand, are more reactive than chlorides and can be used if a given amine is too unreactive. Acyl iodides are almost never used because these are unstable and difficult and expensive to prepare and tend to yield many byproducts resulting from redox chemistry. The fact that acyl fluorides are less reactive than chlorides or bromides indicates that the rate determining, that is the slowest step of the benzylation of morpholine, is the cleavage of the carbon-halogen bond and not the addition of the amine to the carbonyl group. The reactivity of amines can vary a lot. Because of the short carbon-nitrogen bond, bulky substituents strongly diminish the nucleophilicity of amines. Also electron-withdrawing substituents, such as benzyl 2-alkoxyethyl or aryl groups, will lower the reactivity of amines. Alpha amino acids and their esters, as well as ethanolamine derivatives, are much less reactive than simple aliphatic amines. On this slide I've listed some representative amines and their nucleophilicity towards cinnamic anhydride. As shown by the examples in the first row, cyclic secondary amines are more nucleophilic than non-cyclic secondary amines. Pyrrolidine is still more nucleophilic than piperidine. The examples of the second row show the impact of increasingly electron-withdrawing substituents. The third row shows how bulky substituents, such as isopropyl or terz-butyl groups, affect the nucleophilicity of amines. Substituted diisopropyl amines or terz-alkyl amines can be really difficult to acylate, even with strong acylating reagents. Finally, aryl and diaryl amines usually react much more slowly with electrophiles than most aliphatic amines. Aryl amines are, however, easier to acylate under acidic reaction conditions. Nitroanilines, for instance, can be converted into amides by carboxylic acids in an excess of phosphoric acid, just like the esterification of alcohols or phenols. One of the more problematic nucleophiles is aqueous ammonia. Ammonia is much less nucleophilic than alkyl amines, such as methylamine, and water can compete with ammonia more effectively than with aliphatic amines. Therefore, a large excess and high concentration of ammonia are usually required to convert acyl chlorides into amides in high yield. In this example, 6.2 equivalents of concentrated aqueous ammonia was necessary to attain 78% yield of amide. In this optimized example, a still larger excess of aqueous ammonia was used to prepare a substituted benzamide. Such reactions are not always easy to perform successfully because too rapid mixing of the reactants can cause a depletion of ammonia on the surface of the acyl chloride and its hydrolysis. This may be prevented by dissolving the acyl chloride in THF and adding this solution very slowly to an excess of cold aqueous ammonia. Further technical difficulties include the clogging of the addition funnel by ammonium chloride and the lack of visibility caused by the dense fog over the reaction mixture. Problematic are also sterically demanding or electronically deactivated amines, such as the one of this example, which was both sterically demanding and electronically deactivated. Here, triethylamine was used as auxiliary base and the reaction was allowed to proceed for 3 days at room temperature. These mild reaction conditions were probably required to prevent cleavage of the hemiaminal. Alpha amino acid esters are also quite unreactive amines, in particular those with tertiary alkyl groups or additional alkyl groups at nitrogen. In this example, alpha-trifluoromethylphenylalanine ethyl ester was acylated by a large excess of an acyl bromide. As auxiliary base, the weakly basic collidine was used to prevent ketene formation and racemization. Highest yields and cleanest products are often obtained with the Schotten-Baumann procedure, that is, by acylating amines in the presence of water. Even anilines can be acylated this way, as in this example. Here, aqueous THF was used as solvent to improve the solubility of reactants and products, and potassium carbonate was the auxiliary base. This is an example of the acylation of an unreactive aniline with chloroacetyl chloride. Here, anhydrous conditions and the weak base pyridine were chosen in combination with ethyl acetate as solvent. This is one of those amides that gives broad signals in the NMR spectrum because of the two only slowly interconverting conformers. This is another example of the acylation of an extremely unreactive aniline. The product belongs to a new class of insecticides, but the difficulty of this acylation is a true bottleneck in their preparation. Here, the acylation was conducted in the presence of a small amount of DMI as solvent, but only reached 45% yield after 8 hours at 100 degrees Celsius. No auxiliary base was used. This is an instance where an acyl bromide might have been helpful. Alternatively, acylation of the aniline with the substituted benzoic acid in the presence of a strong acid could also be tested because 2,4-dinitroaniline has been acylated successfully this way. You can have a look at the precise conditions in part 4 of this playlist. Lewis acids such as aluminum chloride can sometimes also help to acylate unreactive anilines. One potential side reaction though is Friedel-Crafts acylation. Here, with an excess of propionyl and aluminum chloride, an almost complete acylation of dinitroindoline was achieved. Surprisingly, no dehydrogenation to the indole occurred. Another way to enhance the nucleophilicity of electron-deficient anilines is their deprotonation. In this example, dinitroaniline was converted into a sodium amide by treatment with sodium hydride in acetonitrile. Addition of an excess of hexanoyl chloride gave a good yield of the desired anilide. As mentioned, acyl chlorides are sufficiently reactive to acylate amines under acidic reaction conditions. The less basic the amine, the easier the acylation of its salts. In this example, aniline hydrochloride was benzoylated directly with benzoyl chloride and benzene, without any auxiliary base, and a high yield of the anilide resulted. Some additional examples can be found in the two references. Trifluoroacetyl chloride is particularly reactive and can be used to acylate aliphatic amine hydrochlorides directly, as shown here. Trifluoroacetamides are stable under acidic conditions but sensitive toward nucleophiles and can be cleaved, for instance, by other aliphatic amines at room temperature. Enantiomerically pure acyl chlorides, such as the one of this example, racemize readily under basic conditions because of the high acidity of its alpha hydrogen atoms. In this case, racemization even occurred upon heating the acid with thionyl chloride. Nevertheless, racemization could be suppressed by preparing the acid chloride with thionyl chloride at room temperature and by conducting the acylation in aqueous DMF and with sodium bicarbonate as auxiliary base. Amino alcohols can be challenging nucleophiles, in particular if ester formation is to be avoided. In this optimized example, the selectivity could be improved by in situ conversion of the acyl chloride into an imidazolide by an excess of imidazole. Despite the anhydrous reaction conditions, no ester was formed. Other bases, for instance pyridine, did not provide for a complete conversion of the reactants, and a smaller excess of imidazole led to the polymerization of the acyl chloride. So, what are the main potential side reactions? As mentioned on the last slide, acyl halides are sufficiently electrophilic to acylate ureas and amides. Thus, an excess of acyl halide can cause the formation of imides, even without the use of strong bases, as in this example. Acyl chlorides can also act as dehydrating reagents and convert amides into nitriles, as shown here. Again, such reactions can proceed under mild reaction conditions and without strong bases. During automated solid-phase peptide synthesis, for instance, unprotected asparagine or glutamine are sometimes dehydrated to the nitriles. Strongly electrophilic acyl halides, such as trichloro or trifluoroacetyl chloride or phosgene, may also act as oxidants and dehydrogenating reagents. In this example, trichloroacetyl chloride converted triethylamine into diethylvinylamine, which was acylated at carbon and converted into an enaminone. The formation of such byproducts can sometimes be prevented by conducting acylations in the presence of inorganic bases and water, like in the Schotten-Baumann procedure. In this example, dealkylation of triethylamine and the formation of a diethylamide only occurred to a minor extent, but tertiary methyl, allyl or benzylamines can sometimes be dealkylated cleanly by acyl halides. Here are some further examples, but many more have been reported. You can also find this reference list in the description of this video. In part 2 of this playlist, we'll have a look at other, less reactive acylating reagents and their use in the preparation of amides from amines. These are often better suited than acyl chlorides for structurally more complex amines. See you then.